Hello.
Good afternoon, Clay.
Hi, hello.
Dr. Clay.
Yeah.
Good afternoon, Dr.
Good
Clay.
afternoon. Hello. Okay.
Okay, Madam will join. We can wait for Madam will join.
Yep. Let's wait for
Okay.
Professor Data for a few minutes. That's okay.
Okay. Okay, Clay, can we start? But
Yes.
whether Madam will join now?
Okay, no problem. Let's start. Okay.
Yeah. So, good afternoon, everyone. Dear participants, I, on behalf of the coordinators and on behalf of Electrical Engineering Department, welcome you in this particular session of the GIAN course entitled Advanced Permanent Magnet Machine Drive Technologies for Transport Electrification and Renewable Energy. I take this opportunity to welcome Dr. Clay. Dr. Clay is with us for last 2-3 days, but I have this opportunity to introduce him once again. Dr. Clay is currently a postdoctoral research associate at University of New South Wales. His research interest includes design and analysis of permanent magnet machines, high-speed motor drives, multi-physics modeling, and parametric optimization. Prior to that, Dr. Clay has received his PhD degree from the same university and is associated with this university for on this particular research ground. So I welcome Dr. Clay and Madam both. Madam is not here at this moment. So I hand over you, sir, this session. Thank you. Please go ahead.
Okay, thank you so much for organizing this. Okay, so let's start. I will start sharing my screen. Okay. Okay. Okay, so I guess in last two tutorial, I just find I had a technical problem because sometimes I will lose audio from you. So when you say something, I didn't hear you. I fixed that. So hopefully that won't happen again. Okay. And also I kind of want to change the way we do this tutorial, because I think most of you are more interested in the workshop, like how to use Simulink and the FEA. So I will focus more on doing the workshop. So we'll go through the knowledge point during we do the workshop. Okay, so we'll spend less time on the PowerPoint. Okay, so hopefully you will like it. The first thing I want to do is to continue the FE workshop, because we didn't finish it yesterday. Okay, so yeah, let's start the FE workshop. Okay, oh, I forgot that. So this is the learning goals of today's tutorial. Okay, so hopefully after completing today's tutorial, I can help you to refresh the knowledge points obtained from today's lecture, acquire knowledge and skill of FEA, learn how to build, solve, and analyze a FEA-based PMSM model, and also learn how to build, solve, and analyze a MATLAB and Simulink-based PMSM drive model. Okay. So let's first start with ANSYS. Okay. So I hope you still remember. So this is the interface of ANSYS, and I have sent the a student version download link to you through the chat window. If you still want it, let me know. I will post it again at the end of this tutorial. And today I actually checked the mesh limit of the student version. I find if we use a model with if we kind of sacrifice the quality of the mesh, so you can still build the same model I'm demonstrating. I'll show you how to set the mesh and reduce the mesh element number. So you can also use your student version ANSYS to solve these Prius motor model. Okay. Okay. So yesterday I introduced how to build a basic model. Today, let's go through that together again. So you can, just in case you forget how to build the ANSYS model. Okay. So again, this is the interface you will see after creating a Maxwell 2D design. Okay. What's the first thing we need to do other than the settings? Do you still remember? So the thing we need to do is actually, the first thing we need to do is to draw the motor geometry, right? So the first thing we need to do is to build the geometric model. Mostly the stator, the rotor, stator model, rotor model, permanent magnets, okay? The windings and the region, okay? We need to also build a region, okay? Because you don't want to solve an infinite large model. So you need to limit the size of the model by building a region, okay? So basically the region is a larger version of the motor segment, okay? It covers every part of the motor model. And also when we try to solve a transient model, we need to also build a band geometry, I'll show you how to do this later. Okay, so the band should cover all the moving parts of the motor. In this case, that is the rotor and the magnet. Okay, and you can draw the motor geometries by simply using these drawing tools. Okay, or you can use the I'm Expert templates. So yesterday, I demonstrated how to draw these geometries using the I'm Expert template. Okay, and if you still remember, if you still remember that, after I build the geometry, it's actually a whole motor, right? A whole motor, 360 degree, right? But, okay, if we solve a whole motor, that will increase the computational load of ANSYS and also our workstation. So normally, we will take the advantage of the motor symmetry. Okay, so we split the model because most of the motors are symmetry and they are periodical. Every pole are the same. So we only need to, for integer number slot distributed winding, normally we only need to simulate one of the pole. We only need to model one of the pole. Okay, but if it's a fractional slot concentrated winding motor, then you need to check. Okay, you need to check its symmetry condition. Normally, you can only simulate half motor. Okay, so you must simulate at least half motor for fractional slot concentrated winding. Okay, and there are other cases. So some motors are not symmetric at all. Okay, so we call them asymmetric motor. So actually 2 years ago, when I go to the ECC conference, I met Professor Bianchi. Okay, he's a very famous professor working in electric machine design field. And in the conference, he presented a very interesting design that is inspired by a butterfly living in Italy. And that butterfly has the wing of the butterfly, wings of the butterfly are not symmetry. So is his motor. Okay, so this is a very beautiful, that is a very beautiful design. And in that case, we can't split the motor geometry at all. Okay, I was trying to find his paper, but I couldn't within the limited time. But if you're interested, you can go to IEEE, explore and search Professor Bianchi and look for his paper. Okay, so this is the second step, taking advantage of the motor symmetry. We only simulate one pole or half motor to reduce the computational workload. Okay. Next, after we have this model, the next thing we need to do is to rename each component. Okay. This helps us to find this component quickly. Otherwise, there could be just rectangular 1, rectangular 2, and when you are working on this, and you may not find the right component, especially when you try to write equations. So rename all of these components to what they are. It's a very good habit. Next, we need to assign material to each of these parts, to each of these components. Okay, so that's what FEA does, like what I introduced and also what Professor Data introduced. So in an FEA, so what we are trying to do is to get as close as possible to the reality, the motor geometry and the motor material. Okay, so first we draw the geometry and then we assign material to each of the components. Okay, so for example, for the stator and the rotor lamination, we need to assign the electrical steel lamination material to these two parts. For the magnet, you need to know what grade the magnet has. Okay, it's N35, N36, N38, or N40. Okay, and the windings are just simply copper. So if you're using commercial FEA software, normally they have a very detailed material library, okay, provided by the material producer. And the data is normally very accurate. But if you are using an open source software, so you may need to build your own material. You need to grab the data from the datasheet of each of these material, manually input, for example, the pH characteristic, the core loss coefficient, okay? But in this case, I'll show you how to find the materials in the library of ANSYS, okay? So this is the first step you need to do, assign material to each of them. Next, normally what I like to do is follow the project manager, okay? Just follow this sequence. See, it tells you the first thing you need to do is to build the model. So that's what we have done in the first 4 steps. Next is to assign boundaries, okay? Professor Data also introduced about the boundaries, the boundary settings of FEA model in yesterday's lecture, right? So if you have a model, okay, based on the symmetry of the real model, then you need to have an independent boundary, and a dependent boundary, okay? That tells the software how you want the whole motor to be constructed. So it's one by one. Dependent boundary next to independent boundary. Independent boundary next to dependent boundary, okay? So it can build a full cylinder, right? And also we need to assign the vector, zero vector potential line, that is the outer edge of the region, okay? Yeah, so that's assigning boundary. So assigning boundary is a very important step of building an FEA model, because FEA actually represents finite element analysis, okay? Finite means limited element, okay? How it can have limited element. So actually finite element is the opposite to our reality, because the reality has infinite number of elements, right? So your model can be infinitely large. You can solve, the physics law exists in the infinitely large space. But in our FEA model, we have to limit our model in a finite region, okay? And we use mesh to divide them to finite number of elements. So that's why it's called finite element analysis. Okay, so assigning boundary. Next step is to assign excitations. That is, give it current excitation to the winding corpus, okay? So I guess we haven't talked about this. I remember we haven't talked about this in yesterday's tutorial, so I will show you how to do this in today's tutorial, right? And sometimes you want to set some special calculations, not special, so some calculations of the model. So you need matrix to solve the inductances, because we all know LA, LB, LC, and the mutual inductance exists as a matrix, okay, mathematically. And the torque, you need to let the model know what torque, whose torque you want to calculate, okay? So that's the situation. That's the time you need to set this. In this case, we want to calculate the torque acting on the rotor, okay? So you need to select the rotor and the magnet, and then assign torque calculation to the rotor. Next, very important step is to assign mesh, okay? Mesh, you need to assign mesh to each of the component, right? And for example, if you think the magnet is more important, you need to give magnet a fine mesh, okay? Normally, we give a low quality mesh to the region, okay? Because there's actually very little field exists in this hole and this area. Most of the field exists in the stator and rotor iron, magna, and copper. Okay. So I'll talk about the mesh settings later. Okay. Then it's the analysis setting. Okay. We haven't talked about this in yesterday's tutorial. I will cover this in today's tutorial. And oh, it's blocked. It's blocked. It's okay. Then the last step is to solve the model and get the report. The first report we need to check is the convergence report, like whether this FE model converge or not. The next is the XY plot. Normally X is time. The Y-axis could be your torque, could be flux linkage, could be inductance, okay? And also you can plot field report. Field report is to plot the magnetic field or electric field on your geometric model. For example, the flux line. So this is the field report of the magnetic flux line exists in this model, in this motor model. Okay, so enough introduction. Let's go to the introduction of the process. Let's go to the ANSYS. All right. So yeah, if you still remember what we did yesterday, so we got this geometry by using the predefined IMExpert templates. Okay, so when we use the template to build the geometry, it's a full motor, a whole motor. Okay, then we need to split it to one pole, right? This is the motor with all the windings, and you can see each pole is the same to the pole next to it, both stator and rotor. So when you split this whole motor model to one pole, you can split it like this. So you can get a full rotor pole, okay, like this. Oh, you can get a full rotor pole. Okay, so this is one of the pole of the magnet, and these two magnets have the same polarity. That means they are, for example, they are both source at the top and north at the bottom. Okay, or source at the top, north at the bottom. So you can split it like this. You get a full rotor pole. You can also split it like this. You get half pole of two poles that are next to each other. So in this case, we have the rotor Q axis aligned to the middle. The previous one has a D axis aligned to the stator model middle line, right? So both are fine, both are okay. Okay, you will get exactly same result using these two models. Okay, in this case, in this tutorial, we are using this model, okay, which is the Q axis in the middle. Okay. And this is the solved model. Okay. Let me disable that. We don't want to see the result. Okay. Yesterday, I have presented to you how to get this geometry and how to assign the materials, right? So let's take a closer look, but I did that in a rush because I was trying to complete everything. So let's take a close look to how to select the material and what properties you need, what characteristic of the material you need to have for these materials. For example, for stator and rotor, we want to select the GFE steel 35GN 300. Okay, so the first two letters normally represent the thickness of the lamination, meaning the lamination we want to use in the motor is 0.35 millimeter thick. Okay, then you need hundreds or even thousands of this kind of laminations to get the rotor stack and the stator stack that is 83 millimeter long. Okay, so that's why it is called laminated rotor, laminated stator. Okay, the last 3 digits, you can see this 270 or 300. This represents the loss property of the material. The higher this number is, more loss will be produced when you use this material. Okay, but also if you want to use a material with a good, with a lower loss property, it will be more expensive. Okay, so in this case, we select this one. You can select the material library for ANSYS by click here. Okay, so normally for electrical steel lamination used in the stator and rotor, I use JFE Steel Library. Okay, it is one of the biggest electric steel producer. It's a Japanese company, and it has electric steel laminations of different thickness, different loss property, different grade. Okay, if it's for magnet, I would use the library provided by Arnold Magnetics. Okay, so these are this is the grade of the magnet. N represent neodymium. That is the rare earth permanent magnet. Okay, 28, 30, or even higher number 33. These 2 letters represent the maximum magnetic energy this material can provide. Okay, so the last 2 letters, or sometimes 1 letter, is the temperature grade of the material. It shows what is it tells you what is the maximum temperature this magnet can handle. So it's normally extreme. So EH represents extremely high, H is high, M is medium. I forgot what these letters represent, but you can Google it online. Okay, so what all these letters represent, but you just need to know it represents the highest working temperature of this material. UH is ultra high. Okay. Okay. So this is how to select the material for electrical steel and magnet. Copper, for windings, it's easy. You just need to use copper. Okay. So that's copper. And okay, just before I finish this part, so let's use magnet as an example. So when for example, for this N40UH magnet, you have HBH curve. Okay, so this is a non-linear BH curve. That means when you use FEA to solve your motor model, okay, you are actually considering the non-linearity, the magnetic non-linearity of the material. Okay, although it is not 100% accurate, but it is so far, I guess, the commonly believed the most accurate method. Okay. Okay. Assigning material, and this is the region I was talking about. Okay. So we have our stator and rotor segment, and then you need to draw a region. Okay. The region need to cover the whole motor model, and it should be slightly larger than that. Okay, so this is our region, and then in this case, we will only solve, the software will only solve the elements, the mesh elements inside the region. Okay, it will consider there's nothing outside this region. Okay. After we assign the boundaries and draw the region, okay, after we assign the material and draw the boundary, next is to create the boundaries. Okay, I have introduced about this, and Professor Data has talked about this in her lecture. So we need to have a independent boundary and dependent boundary and the zero vector potential line. Okay, in this case, this is a magnetostatic model, but we still want to know, if you want to know the torque acting on the rotor, you need to select the rotor and the magnet and right click on parameter, assign torque. Okay. If you click talk, assign talk, you will get this window pop up. Name talk, that's fine. Axis, that is a talk around that axis, that positive direction. Just click OK. Next is mesh. Okay. So I used to normally, when I'm working on my own workstation, I will use a finer mesh than what I'm showing here. Okay, but I did some experiment, and I find if you use these numbers, the mesh quality, okay, you can have a model with less than 2,000 mesh triangles, meaning you can use your student ANSYS to solve this model. Okay, so what numbers I used? First, for magnet, so to assign the mesh on magnet, you need to select the magnet while holding control, right click on them, assign mesh on the selection, length based. Okay, then you will have this window. Okay, so name it as magnet, use 6 mm here. Okay, similar for the rotor, you need to use 10 mm. Okay, and for the stator, we use surface approximation, but with manual setting. We only consider the normal deviation of 30 degrees, meaning we divide all circles or curves by 30-degree arc angles. Okay, aspect ratio 5, use this setting, and eventually the mesh you get will have less than 2,000 elements. Okay, then you can solve it, use your student version ANSYS. Next is the analysis setting. So now we have this setting there, but at the beginning, you won't have this setting. What you need to do is to right click on analysis, add solution setup. Okay, then you will get this window. Let's look at the settings I've already done. Okay, so this is the general settings, the maximum number of passes and the percentage error. Okay, so this is the standard you set for this model to be considered as a converged FE model. Okay, the percentage error is actually how can I explain this? Okay, so FE's analysis is an iterative process. It will first try to build a mesh, apply the equations in this mesh, and it will calculate the total magnetic energy, okay, of the model. And then it will refine the mesh, meaning it will make the mesh element smaller, okay? And then it will recalculate the percentage. It will recalculate the total magnetic energy. And compared to the previous one, you will get the percentage error, okay? So it will keep refining the mesh, okay, until the latest one, the energy of the latest one is almost the same as the previous one. And the percentage error is lower than the value you set here, okay? Okay. This is how much you want to refine the model, okay? So let's say if the first time it passed, you get the result, okay? Then next time it will refine the mesh by 15%, okay? Meaning it will increase the mesh quality by 15%, okay? Minimum number of passes, that is, it need to pass at least twice to get to be considered as a mesh design that passed the preliminary examination. Okay, and then you need to have at least one result that converge. Converge meaning the error percentage is less than 0.5. I know it's a bit abstract, but after we solve the model, I will show you the refinement and the iterative process. Okay, so that will help you to understand what is this refinement, what this converge means, and what is this percentage error means. Okay, so for now, you just need to know for this model, these are the values we use. Okay, we use for this model. Okay, after we set this, then we can right click on the setting and analyze it. Okay, so normally it will take a few minutes to complete the analysis. I have already solved this model, so we don't need to analyze it again. Okay, now we'll look at the convergence data together. Okay, so this is the result. You can see we only this model because we set a relatively low, a high percentage error, that is 0.5%. So it only took it two pass to converge. Okay, so in the first model, in the first attempt, it built a model with 838 triangles. Okay, so that's the triangle mesh number. Okay, it passed the test, and this is the total energy of the model, the total magnetic energy, okay, which is B times H. Okay, and then the second time when it passed, it refined the mesh by 15%. Okay, meaning it increased the mesh element number by 15%. And this time, even we refine the mesh by 15%, the total energy only changed a little bit. Okay, how much it changed? It changed approximately 0.2%. 0.2% is lower than the standard we set. The standard we set is 0.5%. Okay, so the software consider this design converged. Okay, so this is a reliable result we can use. Okay, so this is what refinement means. Refinement means how much it increased the mesh element number. Okay, it call it triangles because it's a mesh with many small triangles. This is the total energy it calculated, and this is the energy error. Okay. Okay. We asked this model to calculate the torque acting on the rotor, but you can see it is a very small number, right? That is because we didn't give this model any current excitation. Okay, so meaning there's no current. Okay, just the magnet in the rotor, but still we have some torque. Okay, so this torque, if will change if you change the rotor position, and this torque is called the Coggin torque. Okay, the torque acting between the rotor and the stator, that is called the Coggin torque. All right, okay, so this is what we can get from the convergence report. Okay, to help you, to further help you understand the mesh operation, let's look at the mesh. Okay, so this is the mesh ANSYS plotted for us. Okay, you can see it divided this model into multiple triangles, and because this area we don't have anything here, we don't have anything here, so in these two areas we have the largest triangles, which is meaning the mesh quality here is pretty low, but that's all right because this is not important. Okay, so normally you need to take a closer look at the air gap, because if you remember, we said this, so the air gap is the most important part of an electric machine. So you need to zoom in and see whether the air gap mesh is fine enough. I think this is okay. Okay, so there's not a 100% accurate standard for examining the mesh quality. So I would say this is mostly based on experience. Okay, so when you do enough FE simulation and you look at the model, you will know whether this is okay or not. Okay, so actually, if you ask me, my personal opinion, if I use my standard to examine this, I would prefer to make the air gap mesh finer. Okay, meaning we need to have smaller triangles in the air gap. But because many of you are using the student version ANSYS, so I guess this is the best setting you can use. So, and we can still get a fairly accurate result. So it is okay. Okay. So this is a mesh. It divides the model into finite number of elements, and each element is a triangle. Okay, it divides everything into small triangles, and it applies the Maxwell's equation, the energy equation, into each of these triangles. Okay, let's say this is the first mesh the software generated, and they calculated its energy to be 50 joule. Okay, to be 50. Then to make it converge, it need to increase the number of triangles, meaning refine the mesh by 15%, and then recalculate the energy. Okay, so let's say the new energy becomes 50.0.1. Okay, then the error is smaller than 0.5%. So it can be considered as a converged model. But if the first mesh gave us an energy of 50, the second one gave us an energy of 55, that means your model did not converge. Okay, so there's something wrong. You need to use a finer mesh. So it will continue the process, increase the mesh element number by 15%. Okay, and then recalculate the energy until the error percentage becomes lower than 0.5%. Okay. Okay, so this, I guess, about the theory, if we talk about the theory of FEA, this is the most difficult part, even for using FEA. So if you have any question, please let me know. Okay, I read yesterday's survey, so many of you find the mesh and FEA theory difficult. If you have any question about it, please let me know. Okay. No? No question? Okay. Then let's continue. Okay, so this is a mesh and how the model can converge. Okay. Now we don't need to look at the mesh anymore. Let's see what we can get from the model. We talked about this yesterday, right? So for an electromagnetic static no load model, the most important parameter or most important performance we want to get from the model is the air gap flux density. Okay, and also the flux density and the saturation condition. Okay, so you can see the model, the whole motor only saturated near the bridges. This is what we want because the bridge need to be saturated to limit the leakage flux, the rotor leakage flux. Okay, the stator yoke, rotor are not saturated, and that's good. Okay, another thing we can get from the magnetic static model is the flux density in the air gap. Okay, so this is the value we can get. So from this, we can know the peak air gap flux density at no load condition is approximately 740 millitesla. Okay, in other words, 0.74 millitesla. And you can use this number to do many calculations, right? Oh, somehow it's frozen. Okay, so the maximum number is 0.72. Okay, but you can see here, this is not a sinusoidal curve. Okay, that is because this is the amplitude. If you want to see the true value with direction, you need to plot it as you need to only plot the radial direction with you need to only plot the radial component of the flux density with polarity. Okay, so if we continue to draw this drawing, you will get a curve that is close to sinusoidal, and you can apply FFT to this curve to get the fundamental amplitude of the air gap flux density. Okay, so this is the most valuable information we can get from a magnetic static model. Next, I'll show you how to solve a fully loaded magnetic static model. Okay, that's very simple. So we already have the one without load, with no current. Then for the new one, we just need to assign current to each of the winding conductor. Okay, for example, this is phase A. You just select this one, right click on it, assign excitation, current. Okay, and because this is a magnetic static model, so nothing moves. You only need to give it one current value. Okay, in this case, for the Prius motor, and this current is the total current running through the slot, not the current running through the copper conductor. So meaning this number is I times the turn number. So for the Prius motor, full load is 1,500 amp. Okay, so this is a peak current value that can running through the slot of the Prius machine, 1,500, and it is positive. Okay, it is already assigned here. For phase B, okay, because 1,500 is a peak value, and when phase A current is a peak value, we know from the 3-phase current equation, phase B and phase C should be half of that. Okay, so negative half of the phase A current. So if phase A is 1,500, phase B and phase C should be minus 750, right? And the phase B winding had the same direction as the phase 1 winding, but the phase 3 winding here, because phase C winding here in the middle of phase A and phase B, the direction should be opposite to phase A and phase B. Okay, that's because, okay, this is phase A. There's 120 electrically 120 degrees between phase A and phase B, and actually the phase C next to this period, the phase C should be here. Okay, another 120 degrees. The phase C winding we have in between phase A and phase B is actually the other terminal, the other side of the phase C winding here. So this phase A is running like this, phase B winding running like this, phase C is running like this. So their directions opposite, positive, positive, negative. Okay. So this is how we assign current to constant current value to magnetic static model. And you don't need to change the rest settings, you just need, and then we can just solve this model. Okay. And we can again check the convergence report. You can find, again, they just need 2 times to pass the convergence examination with the energy error lower than 0.2%, which is good. Now we get a much higher torque. Okay, remember previously it's 0.00 something Newton meter. This time we get 63.424 Newton meter. Okay, so that is because this time we have the interaction between the stator MMF and the rotor magnetic field of the rotor magnets. Okay, so this is the loaded torque, but it's again, but still, this is not the final value because this is only the torque generated by one pole. You need to multiply by 8 because we have 8 poles. So the final torque value should be this number times 8 to get the torque value of a full motor. And also, because this is a 2D model, by default, it assumes the rotor length is 1 meter. Okay, so also, so to get the real torque value, it should be this number times 8. Okay, because we only simulated one pole times 83 point something millimeter, that is the real length of the motor, divided by 1000 millimeter, that is 1 meter. Okay, so that's how you get the torque. Okay, so we already checked the flux density and the flux line of the no load condition. This is a new flux density and the flux line at the loaded condition. Okay, so you can see in this case, not only the bridges are saturated, the stator tubes are also saturated. Okay, meaning we will have a very high loss in the stator. Okay, and that's a reason why the Prius motor cannot operate at the maximum power for a very long time. You can only operate at the maximum power for 20 seconds. If you operate for a long time at the maximum power, the stator tubes and the windings will generate a huge amount of heat, and that will cause potential damage to the motor. All right, so this is the magnetostatic model. Next is the most interesting one. Okay, so we want to solve the transient model. The transient model is the one that is very close to the real machine. Okay, because in the transient model, it simulates the motor condition when the rotor rotates at a constant speed. Okay, so we need to simulate the real current excitation and rotor rotation. How we do that? To do that, you need to first change the solver. Remember, we are still using the magnetic static solver. Okay, so right click on it, solution type. You need to change it to transient solver. Okay, we cannot use a magnetic static solver anymore. You need to use the transient solver. Okay, use the transient solver, and we need to change the current excitation we assign to the windings, because previously it's a static model. The rotor does not rotate, but this time the rotor will rotate. So the current needs to change with time. Okay, so we need to delete the previous current settings. Okay, and instead we need to create new current settings. Okay, like this. Okay, so how to do that? First, we select all the coppers. Okay, for all 3 phases, right click on it, assign excitation, coil. Okay, so we want to build them as a coil model. So click coil, don't change the name. The Prius motor, each coil has 9 turns. So we put 9 here. At this time, we keep the polarity as all positive. It will automatically generate the coil for each phase. Okay, but you need to remember phase A and phase B polarity are positive, but phase C should be negative. So we change the polarity of phase C to negative. Okay, you don't need to memorize this. Like, you don't need to memorize which one is positive, which one is negative. Okay, so when actually, when you design the motor, you should already have the stator winding arrangement, okay, ready for you to build into the model. You just need to look at your drawing, okay? The drawing should tell you what polarity is for this phase and what polarity is for that phase, okay? Okay, so now we have these windings. The next thing we need to do is to, these are coils. We need to create windings. So we click here, create winding. Sorry, that's too quick. Right click on excitation, add winding. So we want to add the phase A winding first. Phase A. The previous motor use stranded wire. So here you need to click stranded. The current value, okay? The current value is actually an equation, okay? An equation of I max, the maximum current amplitude times sine omega t plus theta, okay? Because we know, if we know the amplitude of a current, okay, we can represent the sinusoidal current curve using I max times sine omega t, right? And this theta is the current vector angle, okay? So this is the current vector angle between the current vector and the Q axis, okay? And when you press stranded, okay, so now you just click OK. Okay, now because the software does not know what I max is, so you need to add variables to the design. For IM, okay, you need to set it to, okay, let me check what is the IM value. Okay, previous machines current amplitude is 250 amp. Okay, so you change the unit to 2 amp. The value is 250. Click OK. It also does not know what is omega rad. That is the omega, the machine speed in radian per second. Okay, so in radian per second, there will be which will equal to the rotor speed in degree per second, right? So omega is degree per second. If you want to convert it to radian per second, you need to times pi divided by 180. It's actually times 2 pi divided by 360, but it's the same. What's omega? Again, we need to calculate omega from the speed of the machine. Okay, the speed of the machine, which is the speed in RPM times per pairs divided by 60 times 360 degree, right? These should not have unit. Okay, omega and motor speed. In this case, we want to simulate the motor performance at 3000 RPM. First, we select none as the unit type, 3000 RPM pole pairs. Okay, pole pairs equals to pole number divided by 2. Press OK. Poles. This is the 8-pole machine, so we input 8. And theta is the angle between current vector and Q axis. Click OK. Okay, now let's double check. Okay, they don't have unit. Okay, don't give this parameter a unit. Okay, because that will affect your calculations. So for any parameter involved in the calculation, define it as a unitless variable, except the one you are going to assign to the settings. So we can only have I max has the unit amp. All right. Okay, so we have the phase A winding, we have the phase A coil. Now we need to add the coils to phase A winding. That's probably too quick, sorry. So right click on phase A, add coils, select phase A and phase B. click OK. It will, okay, move phase A and phase A coils to phase A winding, and repeat the process for phase B and phase C. Okay, the only difference is, remember the equation for phase A current, that is I max times sine omega t, right? What is the equation we need to use for phase B and phase C? Same equation, plus and minus 120 degree, right? Because phase ABC are 120 degrees separated. Okay. So I just do one more example at winding, phase B, and the current value of phase B is, except we need to minus 2 pi divided by 3, which is 120 degree. Okay, then click OK. Oh, sorry, it's frozen again. Bear with me for 1 minute. Okay, now we have phase B winding. We need to assign coil. It's not assign, sorry. Add coils. Select phase B. Click OK. So down for phase B. Similar for phase C. Okay. I won't do that because I have one that is already solved. So let's not waste your time in this tutorial. Keep doing that. Okay. So after you set the excitations, another thing is, if you still remember, okay, we need to make, this is the transit model, meaning the rotor need to rotate. Okay. To rotate the rotor, we need to create another geometry, okay, that is called the band. Okay. Okay. You need to create another geometry, band. So your band should cover the rotor and the magnet, and it should, the outer radius, the outer edge of the band should equally split the air gap. Okay, meaning the diameter of the band should be outer radius of the rotor plus the outer radius of the stator divided by 2. Okay, the radius of the band. Okay, so how to draw the band? You just draw a line like this from the original point to the middle point. Okay, double click. Okay, draw a line. Okay, here you need to put this number 80.575, which is the average value of the rotor radius and the stator inner radius. And you select this line, you swap around zeta axis, swap by 1 degree. Sorry, not by 1 degree, by the arc angle of 1 pole, which is 45 degree. Okay, so if you swap by 45 degree, you will have this band. Okay, so this is how you draw the band and cover the rotor. After you draw the geometry of the band, you select it, right click on it, assign band. Okay, but in this model, I've already done that. So let's go to this one. So after you click assign band, you will have this window pop out. Okay, what type of motion you want to give it to this band? It is rotation. Okay, by default, it is translation. You need to change it to rotation. Okay, and then select the rotation axis, which is zeta, positive. Okay, the initial angle of the model should be 30 degree. Okay, So meaning when phase A current is at its maximum value, okay, you should have the Q axis aligned to this point. Okay, I can show you why we need to do that later. Okay, the mechanical speed, then you need to give it a mechanical speed of 3000 RPM. Okay, now I'll show you why we need to give the rotor an initial angle of 30 degree. Okay, not this model, sorry. Okay, so this is the full motor model. Okay, and this is our phase A winding. The phase A winding will be like this, right? So if we draw vector, the phase A vector is here, right? So at the beginning, we want to align this D axis of the pole with the center of phase A, right? And this angle is 30 degree, right? So you need to align your rotor with the stator winding. So that's why we need to rotate this rotor by 30 degree, okay? Okay. Did you get this point? If you don't fully understand this, please let me know. I can explain this again. Nope. Okay, then let's go back to the transient model. Okay, so you need to, in the motion setting, okay, how to help this motion setting, we need to assign band to the band geometry, rotation around z-axis, positive direction, initial angle 30. 30 is to align the rotor with the stator. Okay, mechanical speed 3000 RPM. And after you set the motion, after you set the current excitation, next is to set the analysis setting. Okay, it is different with the magnetic static settings because this time the rotor will rotate as time goes on in the simulation. Okay, so we need to set the simulation period to be 15 milliseconds. So this number is calculated from the speed of the rotor. So this is the time that required for the rotor to complete one period. This is a time step. So we will simulate the field this time step. Okay, at each step. Okay, and if you want to see how the field varies, you need to set the field at each step and change this nonlinear residue to 1 × 10⁻⁻⁶. Okay, this helps you to get an accurate result. Click OK, analyze it, and then you will get the result. Okay, the transient model takes a longer time to be solved. And again, this model is already solved, so we don't need to wait for that. Let's look at what result we can get from the transient model. All right. Oh, forgot another important thing. Sorry. Before we do the analysis, there's another very important thing we need to set. Always forget to mention that in the training session. Okay, so after we set the motion and the current, another thing very important for us to set okay, is the symmetry. Okay, remember, if you still remember this, so for the magnetic static model, you need to manually multiply the torque of one pole by the symmetry multiplier. Okay, but this time you can just set it here, 8. Then the final result will be automatically calculated considering we only simulated one pole of 8 poles. Okay, and also you can set the model depth, which is the rotor length and the stator length. The Prius motor, the stack length is 83.82 millimeter. So we set it here. It is not skewed, so we don't need to use a skewed model. And another thing very important, we want to calculate the inductance of the machine. We want to calculate, you can either calculate the apparent inductance or the incremental inductance. That is inductance calculated using 2 methods. They are both correct, but normally the apparent inductance of FE model is closer to the experiment measurement, okay? Incremental is normally used in simulations, like Simulink simulation, okay? So we use apparent setting. So we want to get the apparent inductance of the motor. Depending on the situation, you can also calculate the incremental inductance, okay? And also another very important feature of FEA transient solver is it can calculate the core loss, okay? We know the core loss, the hysteresis loss and the eddy current loss, the only appears when we have a wiring current and the wiring magnetic field. So you can only, that's why you can only get the core loss in the transient model, okay? We have the core loss property of the material for stator and rotor. So we check these two. For the rest ones, we don't have the loss property in the material. So even you check them, it won't affect the result. So just check stator and rotor, click OK. It can also estimate the eddy effect, the eddy current loss in solid conductive part. In this model, that is our magnets, because magnets are conductive and they are solid, and they are normally solid pieces. But sometimes people also use segmented magnet. So in this model, we only select PM1 and PM2 to calculate the eddy current loss. After you complete all of this, you can solve this. You can solve this model. Okay. You don't need to memorize this process because I will send you the instruction after today's tutorial. And okay, so you can download the student version ANSYS, follow the instruction in the menu, and it's a guide step by step of building the Prius motor and solving it. So you don't need to memorize all of this. Okay, so this demonstration is just to fool you, is just to help you understand the meaning of each operation. Okay, after we set everything, we solve it. Okay, then the first parameter, very important performance motor we can get, is the torque. Okay, so we get that when the motor operates at 3000 RPM, when we supply the maximum current to it, it can generate a torque of around 240 Newton meter. Okay. Remember, this motor, it is claimed that on the report, this motor can generate 400 Newton meter, right? A peak torque, 400 Newton meter. Okay, that is when we overload the machine. Okay, so we give it a current that is much, much higher than its continuous rating current. Okay, so we can use this motor to generate 400 Newton meter if we increase the current. But when you overload the machine, the machine can only operate at that situation for a very short period. For Prius motor, that is 20 seconds. except torque. So torque, we can get its average value. Okay, you can export to Excel file. Okay, and also you can export it to, remember you can export, okay, no. So you can only export it to Excel file. You can export it to Excel file and import it to MATLAB and do whatever calculation you want to. You want to get the average, you want to get the IMAX value, or you want to get the peak-to-peak value. Okay. We can also do that here in the report setting. We want to see the average value. Just change Y to mean. Mean is average value torque. Okay. Add trace. Okay, so this is our average torque. You can see it's approximately 440 Newton meter. Okay, you can also use other functions listed here. For example, max, that gives us the peak value. Okay, similar to MATLAB. Very importantly, you can get the three-phase inductances. Okay, for example, this is our phase A self-inductance. Like what we learned from the lecture, the inductance, the self-inductance varies with time. It actually does not vary with time, it varies with the rotor position. Okay, so this is how it varies with the rotor condition. Okay, these are the mutual inductances. Okay, and if you still recall, if you can recall from the lecture, the relationship between self-inductance and the mutual inductance is L equals to minus 1/2. So mu equals to 1 divided by 2, minus 1 divided by 2, self-inductance, right? Meaning the amplitude of mutual inductance is approximately half of the self-inductance, and it is the case, very close, not exactly, but very close. You can see the self-inductance of phase A is around 1.1 something. Okay, the mutual inductance is about minus 0.5. The amplitude is approximately half of that. Okay, so this is how you relate your FEA result to the theory and the analytical results. Okay, inductances, flux linkage. So these are the three-phase flux linkage of the machine. If you perform DQ transformation, you can get LD and LQ. Okay. Three-phase induced current. Okay. So this includes the current induced by the rotor magnetic field, which is the back EMF, and also the current on the resistance, the stator resistance, and the stator inductance. Okay, so this is not the back EMF, this is the induced voltage. Also, from FEA, you can get the core loss. Okay, the core loss in the stator and rotor. So the red line is the core loss. Okay, it's actually the sum of the eddy current loss, the hysteresis loss, and the excesses loss. Okay, if you sum these three together, you can get the red curve. But in total, that is represented as the core loss. Okay, for this machine, you can see at 3000 RPM full load condition, we have a core loss around 600 watt. Okay, that's quite high for the machine, but normally this type of machine is liquid cooled. Okay, so we have a water jacket that can help us to dissipate the heat generated by this core loss. Okay, also we can have the solid loss. Solid loss is the eddy current loss in the magnet. Okay, in ANSYS it is called the solid loss. If we have the core loss, if we have the solid loss, we can estimate the copper loss. Okay, if we have the resistance, if we have the phase resistance, we have the copper loss. So the total loss will be core loss plus solid loss and copper loss. And if we have the total loss and the output torque, the speed, you can have the efficiency of the machine, right? Okay, so we can have the efficiency of the machine. So these are the basic performances and parameters we can get from a transient model. Okay. And also you can plot the flux density distribution, the flux line, and the magnetic field vector field plot. Okay, just select the geometries, right click on it, field. Let's see, we want to see the magnitude or objective. You need to go to C solution. Okay. Okay, so this is the magnetic field distribution of the motor at the initial time. Okay, so you can see the field plot as a figure or an animation. You can animate it. Okay, so this may make my computer frozen, but it was it. So let's wait for it. It will show you how the magnetic field wire is when the rotor rotates. Okay, while we are waiting for this, I want you to download the Simulink model prepared for today and tomorrow's tutorial. Okay, please use this link to download the Simulink model. Please let me know whether it works or not. And please let me know whether you can open the Simulink model or not. Okay, so I exported my model as Simulink and MATLAB 2016A. Okay, I hope everyone has MATLAB with version number higher than that. Okay. Right, okay, so this is the animate. Oh, actually, it's better to have it in this time as plotted as a full model. Okay, my computer's frozen again, but please go to the shared Google Drive and download the Simulink model. Bear with me. Okay. This is the only thing I can't solve it in advance, so we have to wait for it. In the meantime, if you have any question so far, please let me know. Okay, now it's ready. Okay, so this shows how the magnetic field wire is when the rotor rotates. Okay, so basically you can see the magnetic flux density pattern of the stator and the rotor rotates together. So this is why it is called synchronous machine. Okay, so we have the stator generates a magnetic field, that rotates with the rotor with the same speed. Okay, and if you only look at the rotor, you will find the magnetic field in the rotor is almost, okay, always consistent. The field in the rotor does not change much, except, you know, when it is passing through the stator teeth. Okay, the stator teeth and the air gap and the slot opening causes magnetic field variation near the rotor bridges. Okay, and the saturation condition and the field strength in the stator tooth also varies because the field rotates. Okay, so this is how you can see the field variation of the motor during the rotation. Okay, now let's stop it. Close it. Another important thing, another important calculation or result you can get from the transit model is, okay, so if you want to get the fundamental parameters or the basic parameter for the motor, such as the LD, LQ, and the magnetic flux linkage and no load condition, you can set the current amplitude to 0. You solve the model, okay? Then you can get you will be able to get, not this one. Oh, yes, it is this one. You will be able to get the phase, the LA, LB, LC, and LAB, and the mutual inductances when there's no load, okay? And from this, you can actually get the LD, LQ of the machine at no load condition, and also from the flux linkage, because at this time, there's no current. These flux linkage are generated purely by the magnet. By doing a DQ transformation, you can get the D-axis and Q-axis flux linkage, okay? Normally, the Q-axis flux linkage is very small, so we use the D-axis flux linkage as the magnetic flux linkage, okay? So from this model, I got the LD, LQ, and flux linkage of the Prius motor. That is LD equals to 2.5 millihenry, LQ equals to approximately 6.2 millihenry. The flux linkage is 0.171 Weber. Okay, so this is how you calculate LD, LQ, and magnet flux linkage of a machine from the FE model. Okay, the phase resistance, you can estimate it from the total conductor length, okay, and the copper wires cross section, the turn number. You can calculate this using the simple equation, okay. Professor Data introduced this in her lecture, so I get this value using that equation. Okay, due to time limit, I won't show how to calculate this number anymore. Okay, it's very easy. That's basically L divided by conductivity times S. Okay, L. The difficult part is how you calculate the total, okay, phase winding length. Okay. Now that's the everything you can get from I prepared for the FE workshop, but it can do more. Not just this. This is just to build in one motor model, solving it and examining its performance. Okay. There are many other things we can do. For example, using this model to do optimization. Okay, to do a basic parametric analysis. Okay, so hopefully if we can still have time left in tomorrow's tutorial, I will introduce a little bit about how to use ANSYS FEA to do motor optimization and parametric analysis. Okay, do you have any question about this FE workshop so far? Any question? No? Okay. Then it's already 8:30. We need to finish we need to wrap up at 5:09 in Sydney time. We still have some time. Has anyone tried to download the Simulink model? Okay. Can you get the Simulink model from the Google Drive?
Any questions, dear participants? Any questions?
Okay. It's okay. If there's no question, I will just continue to introduce to work on the workshop of the Simulink model, the drive model. Okay. So if you open the shared Google Drive, okay, using the link I sent to the chat window, you can download this Simulink model. Okay, this is a model we have been using in our lab. Okay, so this is a very basic FOC drive model. Okay, for IPMSM. Okay, I also included the sensorless control module in this model, but we won't talk about it. We won't use it for this tutorial. But if you're interested, you can open it and look into how the sliding mode observer sensorless control is done. Okay. Now let's look at this model. Okay. So in today's lecture, you have learned about the basic PMSM drive system, right? So first we get the DC supply, or we can get a fixed frequency 3-phase supply. We use rectifier to get DC. We supply the DC to the 3-phase inverter, okay? 3-phase bridge inverter, which consists of 6 switches, okay? And these 6 switches are controlled by the controller using SV PWM, okay? And it controls the current we supply to the motor. From the motor, we can measure its 3-phase current. We can measure the DC bus voltage. We can also use encoders to measure the rotor position. These are the most important parameters we need to measure from the motor in order to control it. Okay, so now let's go back to the Simulink model. Okay, in the Simulink model, it is very similar to what you have seen in that block diagram. It's just all the inverter and PMSM is hidden in this block. If you open it, you can see, okay, so these are the hardwares we have in this Simulink model. This is the 3-phase inverter, and this is our permanent magnet synchronous machine. Okay, double click it. Okay, these 2 modules, if you want to use these 2 modules, you need to use this Samescape library. Okay, Samescape, power system. Okay, and then from the machines, you can get the permanent magnet synchronous machine. Okay, so these 2 modules comes from the Samescape library. If you open it, these are the basic settings for the machine: 3-phase, back EMF waveform, sinusoidal. This is the ideal situation. Rotor type, silent pole. Mechanical input is the torque. So if you want to give the motor a load, you need to give it in the unit of torque in Newton meter. And the basic parameters we can give to this motor is the phase resistance, LD, LQ inductances, flux linkage, and the mechanical parameters, the inertia, the damping ratio, pole pairs, and static friction. Okay. But what's really inside this PMSM machine model, okay, that's actually everything we learned from today's lecture and the previous lecture, okay? Inside the Simulink model, it's actually very simple. It's just the DQ equivalent circuit model, okay? If you supply IDIQ to the model, what voltage you can get, okay? That is calculated using these two equations. And also, okay, if you supply IDIQ current to the model, what torque, what is the developer torque you can get from that. And also you need to have a motor motion mechanical model, okay? That is the new speed and position of the motor is a function of the torque, the inertia, the damping ratio, and the current speed and current position, okay? So we won't go deep into the motor motion equations, but if you're interested in this, you can go to read this book, okay? It has a detailed introduction of how the Simulink motor model is built, okay? So this is what's inside the Simulink motor model. And that's why for that model, you need to let the Simulink know what is LD, what is LQ, what is RS, flux linkage, PM flux linkage, J, the inertia, the damping ratio. Okay, so all these parameters, okay, are listed here. Okay, we got the LD, LQ, and the PM flux linkage from the FE model. Okay, which is this 3 number. We calculated its phase resistance. Okay, the inertia is 0.5 times the total mass of the rotor times the square of the rotor radius. Okay, so these are the basic parameters we need to let the Simulink model know. RS, LD, LQ, flux linkage, inertia, and the damping ratio, not friction. Sorry, the damping ratio. Okay, so normally we use a very low damping ratio because the bearing, we assume we have a very solid and hard contact between the rotor and the shaft and the motor frame. So once you have these basic settings, you can have your motor model ready, your motor drive model ready in the Simulink model. Okay, so this is how we set this one. And to this block, okay, because this block is we are using this block to represent all the hardwares of our inverter and motor, okay? So the input of this block is just the gate signal. The gate signal we want to provide to the inverters, okay? And what is the load we want to apply to the motor. The output is the rotor speed in radian per second that is measured. In reality, it will be a speed measured by encoder, the position measured by the encoder. The output torque, we may know the output torque if we have a torque transducer. Okay, the 3-phase current, you need the 3-phase current. So normally for motor drive, we will have at least 2 current sensor to measure phase A and phase B, and phase 3 will be, because IA, IB, IC equals to 0, so we can calculate IC. So ABC phase current will be measured. And we also need to know the DC bus voltage. So these are the input to the inverter and the output of the machine. This is very close to the reality, the real case situation. If we have a motor in the lab, you want to drive it, these are the signals you can get from that. Okay, again, it's very close to the end to this tutorial. I will just briefly introduce what each of these blocks does, and you can download this model, open it, explore what they are, and play with it, okay? We'll continue this in tomorrow's tutorial. Okay, so after we get the three-phase current, position of the rotor from the motor, from the sensors, okay? The first thing we need to do is normally to do the ABC to DQ transformation, the DQ transformation, as you learned from the lecture. Okay, so inside this block, it's the clock transformation and Park transformation from ABC to DQ. Okay, and this is the decoupling module. Okay, Professor Data also introduced about the decoupling. That is, the VSD and VSQ are actually an equation of both ID and IQ. Okay, but we want to decouple VSD and VSQ from one of the current to simplify the calculation, not simplify, to make the controller works faster. So this is a decoupling module. If you open it, you will see equations exactly the same as the one Professor Data introduced to you in the lecture. So this is a decoupling module, and this is a new VD, VQ we get from that. Okay, and after we get the RSD, RSQ, VSD, VSQ, the speed, okay, then we need to apply the control algorithm. This is the block, okay, that includes all the control algorithm. Okay, this is the IFOC control algorithm. As introduced in the lecture, we have 3 PI controllers: the speed controller, IQ controller, and ID controller. Okay, this module only includes the MTPA trajectory, and it is written in this block. Okay, based on the IQ, what is the ID? Okay, for a certain speed, using the MTP trajectory calculation equations. So this is our control algorithm from the speed and the measure speed, the speed reference, measure speed, the speed error, the first speed controller, we get IQ reference. Using the calculator, MTPA, MTPV, or flux weakening, we calculate the ID reference. And the real ID and RQ are controlled by these 2 PI controller. Okay, to get the required VQ and VD to generate the ID IQ we want. After we have VSD and VSQ, we need to supply the values to the SVPWM generator. Okay, Professor Data also introduced this into this lecture. Okay, so SVPWM generator basically is we have, okay, 4 inverter with 6 switches. We have 8 possible switching status. Okay, okay, and we need to divide when the voltage vector complete 1 full circle, that is 1 electric period. So we need it to go like this circle. Okay, that means we need to pass through these 6 vectors. For each of the vector, what switches we need to control. Okay, and what is the duty cycle we need to supply, we need to give to each of the switch. Okay, that are all covered into this lecture. Okay, and if you compare to this lecture and this module, you will find all the equations you learn from today's lecture in this block diagram. Okay. After that, we can get our gate signal. That is the duty cycle of each switch. Okay, so this is how it works. Yeah, don't have the time to show you the result, but we can continue tomorrow. Okay, now let me wrap up. Do you have any questions for today's tutorial? Okay, no? Okay, I'll type my email address in the chat box. If you have any question about today's tutorial or the previous tutorials, you're welcome to send me an email, any question about the tutorial or the model. Okay, so that is my email address. And now let's go to the quiz. Today's quiz. Okay, happy time. Please scan the QR code or click the link to open today's quiz. Let me know if you can open, whether you can open the quiz or not, okay? Oh, yes, sorry. This is the quiz link. Please keep the Google Drive link, okay? I will upload the FEA model instruction into the same folder.
Dr. Clay,
Yes,
can you stop sharing the screen? I have to take one photo. Participant all this. Okay, Malaka sir.
Yes, sir.
Malaka sir.
Yes,
Please,
yes, sir.
ask them to,
Yeah. So thank you, Dr. Clay, for giving a lot of effort in this session. So I would like to thank you.
thank you for
Now all
listening.
participants. Yeah. So I would like to request all participants to turn on your camera so that a video clip can be taken. Screenshot.
Hello, everyone.
हो गया अभी क्विज आ गया क्या?
Malakar, you can stop. So thank you, madam. Thank you, Dr. Clay, for this nice delivery on this tutorial class.
Thank
Hope
you.
all the students, all the participants learned a lot. Okay. Thank you.
I want to say something here.
Yes, madam.
To the participant, I think that if you be a little bit more interactive, it could have been better. So if you could ask questions and things when he was presenting, because we don't know what you are doing, right? Sometimes it's difficult. That's why for future, if you do an online course like this, please be more interactive. Don't be shy to ask questions. Don't be shy to stop us in our presentation.
Yes, it's very scary, just talking yourself and no one speaking back to you. But yeah, I understand that. So when I was a student, I also don't like to speak in tutorial and lectures. That's okay. Okay, but you can still message me or send me email if you have any question about the tutorial content, about the softwares, or you're interested in what we are doing at our research group. Send me or Professor Data an email. So we are very happy. We will be very happy. We want to talk with you, yeah.
Okay, then see you all of you tomorrow morning, the last one. Yeah.
Thank you,
Bye.
madam.
Bye.
Thank you, Dr. Clay.
Bye.
Thank you.
Thank you,
being with
madam.
us.
Okay.